We're now going to change gears a little bit and talk about Lewis acids and Lewis bases, which is actually another kind of acid-base theory. It's a little different from the Bronsted acids and bases we looked at in chapter 14, but there's a lot of cool things you can do with Lewis acids and bases that you wouldn't normally expect. Now, the picture of the molecule there is a compound called nickel bis dimethylglyoximate, and we'll talk about how to figure out this name in a later chapter. Don't worry. However, for us right now, the important part, the very middle atom, that's the nickel. And you have essentially two dimethylglyoxine molecules. Bis we'll see is a prefix for two. And so those molecules are kind of wrapped around there, the nickel. Now, a couple of things. You'll see here that there are some some single arrows. This is a special kind of a bond that happens in Lewis acids and Lewis bases. And so those arrows, those one-directional arrows, those are examples of Lewis acid, Lewis base interactions. At the very top and at the very bottom, those dotted lines, those are hydrogen bonds. The white hydrogens are connected in some way to the oxygens on the other molecule. That actually tends to stabilize this molecule, which is pretty cool. This nickel bis dimethylglyoximate compound is kind of cool, and you will be making it in lab. In the right-hand side are some pictures from some students from the last couple years. They're holding in their hands there either a test tube or a cylinder with this red compound. It's really a cool compound. You'll like it. But anyway, we will talk about this and make it in future lectures. But let's talk about Lewis acids and bases and how you can make these kind of compounds. So first of all, we have to talk about what a Lewis acid is and what a Lewis base is. And a Lewis acid is an electron pair acceptor. So it's an atom, usually a central atom, that has room for extra electrons. And boron, aluminum, gallium, sometimes beryllium, and lots of the metals, they have orbitals which are empty. And so if you have something with extra electrons, you can push them into one of these empty orbitals and make that happen. Way back in the molecular orbital and valence bond section, we talked about how BF3 is sp2 hybridized, and the boron had an empty 2p orbital. If you remember this, cool, and if you don't, it's no big deal. I can help you remember it. But anyway, the important part here, boron has an empty orbital for electrons. It'll accept the electron pair from another species. A Lewis base is an electron pair donor. It's going to be an atom, usually with a lone pair or two on top of it. And ammonia right there has a lone pair. So it's going to be able to donate this lone pair into a Lewis acid, which can accept the lone pair. So this is the idea of a Lewis acid, Lewis base. It's a lot different from Bronsted. You have nothing to do necessarily with hydrogen. Lewis acids accept the lone pairs. Lewis bases will donate the lone pairs. Lewis bases, again, will be atoms with a lone pair or two on them. Nitrogen is a great Lewis base, sometimes oxygen, etc., etc. Lewis acids are usually boron, aluminum, gallium, or the transition metals. All of those have empty orbitals.
Boron trifluoride is a Lewis acid because it has a deficiency of electrons. Ammonia acts as a Lewis base by donating its lone pair of electrons into BF3's vacant valence orbital. The product of this Lewis acid-base reaction is a single molecule with a new bond, called a coordinate covalent bond, because both the electrons for the bond come from only one species.
In that nickel dimethylglyoximate molecule we looked at earlier, there were several examples of these arrows that were coming from one atom to the other. And now we know where they're coming from. If you see one of those kind of arrows, that's what they call a coordinate covalent bond. It's a coordinate covalent bond because the electrons are coming from one atom and pushing into the other atom. So most bonds, you've got an electron on each atom, they come together to make a bond, and that's good. These kind of bonds, both electrons come from the same atom, and they push themselves into the empty orbital of another atom. So that's why it's kind of cool. Sometimes these types of bonds are called Lewis acid-base adducts, and that's another term that's used sometimes for these kind of things. However, like all things, this will change the geometry. So BF3, which was trigonal planar, if you remember back from electron pair geometry of trigonal planar will actually change to tetrahedral as that fourth pair is pushed in. So it's an amazing process, and some of these are very, very stable. In this question, it says, which of the following is a Lewis acid? Okay. And Lewis bases will have lone pairs on them on one of the atoms, one or more of the atoms. But the Lewis acids will be things like boron, aluminum, gallium, as well as the transition metals. So if you look here long enough, you can see the answer B, silver plus, in that silver compound, that's going to be a great Lewis acid because silver is a transition metal. And transition metals usually make really great Lewis acids. The other three answers there are all compounds with lone pairs. So methylamine is answer A. That nitrogen has a lone pair. On C, carbon monoxide, both the carbon and the oxygen have a lone pair. That's going to be a great Lewis base. And the last one there is hypochlorite, the active ingredient in bleach. It has lone pairs on both the chlorine and the oxygen. That's going to have all kinds of lone pair Lewis base kind of possibilities. So the best answer here would definitely be B. Transition metals, boron, aluminum, gallium, great Lewis acids. And again, Lewis bases will be compounds with at least one lone pair on them. So if you have a complex ion, what that means is you have at least one Lewis base pushing itself into one, at least, Lewis acid. And this is real common with transition metals. I mean, really, really common. You can argue that anytime a transition metal dissolves in water, waters kind of surround it. So in the right-hand side there, that cobalt has 6 waters around it in an octahedral fashion. The cobalt is in the middle, the waters are on the outside. And notice it's the oxygen that's connected to the cobalt. Because oxygen has the lone pairs, it's acting as the Lewis base, and the cobalt, like all transition metals, usually has empty orbitals acting as the Lewis acids. So we would call the COH2O6 3+ a complex ion. It's not just a normal, like say cobalt 3+ or sodium +1, a regular ion. This is complex because there's Lewis bases around that Lewis acid, and the whole thing has a charge. In the lower corner there, you have a copper with 4 ammonias around it and a +2 charge. So that's also considered a complex ion. The ammonia is a Lewis base. It's pushing into the Lewis acid copper. You can see even the arrows on that diagram. The whole thing has a charge, so it's an ion, complex ion. All the metal ions form complex ions with water. A lot of them have 6 waters, some have 4 waters, but they're going to have some kind of waters around it. Transition metals are great for making these complex ions, which can be both good and bad.
In the test tube is a solution of copper sulfate. When we add a few drops of ammonia, the ammonia acts as a Bronsted base and causes the precipitation of solid copper 2 hydroxide. The solution turns a cloudy blue. If we then add a much larger amount of ammonia, the solution turns a very dark blue. The precipitate dissolves upon direct reaction with ammonia molecules. The ammonia has donated its electrons to the copper ion, and so now acts as a Lewis base. Ammonia is a Bronsted base and produces hydroxide ion in solution that can lead to formation of solid copper 2 hydroxide. With additional ammonia, a Lewis acid-base reaction occurs.
So imagine your boss says, hey, make me some copper 2 hydroxide, CuOH2. And you're like, no problem. Most hydroxides are insoluble, so that means they form solids. You'll start with just copper 2+ ions, add a little bit of ammonia, which is a source of hydroxide. No problem. You add a little bit, copper 2 hydroxide. Now in the lower left-hand picture, the lower copper, the lightest blue, that's copper ions. All right, and copper is pretty water soluble, no problem. And if you add a little bit of ammonia, you'll add some hydroxide, and that'll make the copper 2 hydroxide, which is kind of a light blue solid they showed there for a second. So you're like, hey, that's really cool, but I need all I can get from my boss. I'm going to add even more ammonia. So you add, and finally this dark blue stuff starts to appear. And you're like, what the? And on top of that, the dark blue is a solution. It's not a solid. Like all your solid goes goes away. And you're like, what the heck? And this happened to chemists so many times. It's not even funny. They'd think, if a little is good, a lot is better. So they'd start to make a compound and they'd add even more of one reactant, and bam, something would happen. The solid would go away, and they had these usually supercharged, supercolored solutions. Nobody knew what happened. So finally, long story short, they figured out this idea of complex ions. And what's happening here is the copper 2 plus reacts with a little bit of ammonia, which has a little bit of hydroxide, to make the insoluble copper 2 hydroxide, which is what you wanted. But if you add extra hydroxide, extra ammonia, all of a sudden, bam, the hydroxide insoluble compound dissociates, and you end up with the much more probable complex ion between copper and ammonia. It's a beautiful dark blue. I love the color of it. However, if you wanted to make this solid, that would be very frustrating. So this is the joy of complex ions. They haunted, especially inorganic chemists, for a long time. They're trying to make some kind of insoluble compound, and they end up with some kind of wild colored solution, which wasn't what they wanted. It was very frustrating. But now we can figure out what's happening and control it appropriately.
Oxygen binds weakly to the iron ion at the center of a heme group in the hemoglobin molecule. In an oxygen-poor area of the body, the O2 is easily removed. Carbon monoxide, in contrast, binds very tightly to the iron and is very difficult to remove. The presence of carbon monoxide makes it impossible for the blood to transport oxygen effectively.
Since you've been watching this video, you have hopefully been breathing. And oxygen goes into our body, and it connects to the iron in heme. And this is a Lewis base Lewis acid interaction. The oxygen has the lone pairs. The iron is a transition metal, so it's able to accept the lone pairs, no problem. And as this heme goes through your body and blood, the oxygen can be released to the areas that need it, and that's really good for their bodies. That's what makes us live, which is really cool. If you've ever been around carbon monoxide, be very careful, because carbon monoxide holds on to the iron much tighter than the oxygen does. So while oxygen will bond and then it will release in our bodies, the carbon monoxide holds on so much tighter and it doesn't let go. So this is why when people accidentally or intentionally then end up ingesting CO, it kills them, all right? Because you can't get the oxygen transported to the body. It's a bad scene. So these are all, though, Lewis acid, Lewis base interactions, of course, some of them being very important. Stay away from carbon monoxide. Lewis acid and base theory helps to explain the amphoteric nature of some metals, especially metal hydroxides. Now, amphoteric just means that they can act as both an acid and a base depending on the situation. And we saw that water does this, so water can make hydronium. Water can also make hydroxide. And at equilibrium, at any temperature, you're going to have water making both. Well, it's more than just water. Aluminum hydroxide is a great example of this. Aluminum hydroxide can act as a classic base, a Bronsted base. It'll react with acid, H+, in a traditional acid-base reaction, making water and some kind of ionic salt. Here we're only looking at the aluminum 3+, but you could have the whole thing. This is aluminum hydroxide acting as a base. However, aluminum hydroxide can also act as a Lewis acid. It can actually take one more Lewis base, a hydroxide, and put it inside. So just like boron could take one more, aluminum can take one more too. So you end up making AlOH4 minus 1. This is an example of a Lewis acid behavior. So aluminum hydroxide is like water. It can be a base. That's what I would argue it mostly is. However, it can also act as a Lewis acid. So it's just kind of cool. Now, AlOH3 I wouldn't call a Bronsted acid, that there's not really any way to get the hydrogens off of the hydroxides. However, it does act as a Lewis acid, which has its own pH effects, which is kind of cool. This picture shows how this can work out. On the far left-hand side, this is aluminum 3+ by itself, all right? And aluminum 3+ is really soluble in water. And when they add just a little bit of ammonia, ammonia is a good source of hydroxide. So this white solid you see right there, that's that's AlOH3 solid. And then depending on what you do with it, it can act as an acid or a base. So on the top part up here, you're adding hydroxide. That's like aluminum hydroxide is going to be the Lewis acid. The hydroxide will force its way into the aluminum, but the solid disappears because most of these complex ions are water soluble. This is the AlOH4 minus 1 ion, and it's very water soluble. It looks like your stuff just disappears. The aluminum's still in there. It's just a complex ion, so that's why it doesn't look like anything happens. On the other hand, if you add hydrochloric acid right down here to the aluminum hydroxide, this will have aluminum hydroxide acting as a Bronsted base. You'll end up making water. The aluminum 3+ will go off, so it can go both ways. This is the nature of amphoteric materials like water, like aluminum hydroxide, and several other kind of similar species. A special type of equilibrium constant can be used for complex ions. It's called a formation constant, and it's given the symbol K sub F. Now, a formation constant is specific for complex ions, and a formation constant, you put whatever goes into the complex ion as reactants, and the complex ion itself is the product. So you can see for that CuNH3 2+ thing, this would be the form. So products over reactants, the Kf, which is down here at the bottom, would have copper NH3 2+ on the top, divided by copper 2+, divided by the ammonia to the 4th power, which is pretty crazy. Now, these Kf values, these formation constants, are usually incredibly product favored. Ks are usually much, much, much greater than 1. And that just shows that, boy, they are ready to go. So if you have a little copper 2 hydroxide and you add too much hydroxide or ammonia, this thing is going to kick in big time because it's so product favored. So you're going to see this reaction pretty readily. So the important part here is that if you see a formation constant, the complex ion is the product in the numerator, and in the denominator you have whatever goes into the complex ion. So in this case it would be copper 2+ and ammonia to the 4th power. Cool. In the Le Chatelier's principal lab, we experienced the ZnNH3 2+ complex ion. It's something that happens. There's also a somewhat common AgCN2-1 ion. Lots of these different things running around. But again, the important part is that the metal will be the Lewis acid, and the bases will be something with lone pairs that are pushing themselves in. So ammonia is a great Lewis base. It's got the nitrogen on it with a lone pair like we talked about. Cyanide is a great Lewis base. Both this carbon and the nitrogen, if you draw the Lewis structure out, have lone pairs. So there's lots and lots of lone pairs kind of running around there. If you wanted to write a formation constant for the AgCN2-1 ion, this is what it would look like. Again, the complex ion is the product, and the ions that go into it will be the reactants. So Ag+ and 2 cyanides, while the product will be the complex ion. Kf here will be, again, complex ion on top, the ions that go into it in the bottom. So AgCN2-1 on top, silver plus on the bottom, Cn-1 on the bottom, squared. Kf comes out to be 5.6 times 10 to the 18th. Again, super product favored. These things are ready to form at just about any notice and stuff. Yeah, very, very large. Expect a complex ion, basically, if you know it's out there. This is a table showing some respective Kf values, and again, you can see they're kind of all over the place. But all of them big. These are all numbers greater than 1, and you can see some of them are quite a bit greater than 1. All of these, to write the expression, the ions that go into it will be the reactants, and the complex ion will be the product. And these are usually written as net ionic reactions. Like, you're not seeing the counter ions. Like, for example, in the AgCN2-1, the silver plus would probably be like silver nitrate. And I would guess the cyanide would probably be a sodium cyanide. But you're not seeing the nitrate or the sodiums. They're spectators and honestly pretty boring to chemists. So that's why they're not usually shown in these kind of contexts. You can use these in some kind of clever ways, however. Silver chloride is a compound that actually will coat glassware once it's formed, and it makes kind of a fuzzy white look on some of the glassware, and maybe you've seen it this quarter in our labs. If you want to get rid of that silver chloride, you can scrub the heck out of it, but you can also use a chemical method, because if you add some ammonia to the silver chloride, this complex ion, AgNH3 2+ will form, as well as some chloride. So this this is actually a pretty cool way to get rid of some of that nasty white stuff. Now, if you want to see exactly what's happening, here's the KSP for silver chloride. And remember, KSPs, this precipitate is the reactant, and the ions that go into it are the products. This KSP is much less than 1, means there's silver chloride solids going to form really readily. No problem. You can combine this with the complex ion, the AgNH32+. Now, this KF value, 1.6 times 10 to the 7th, you can add them together, silver plus 2 ammonias, making complex ion, as well as the KSP expression. And I bet you can maybe see where we're going here. We're going to add these two expressions together. We're going to ditch the silver. Silver plus is a product in the first one, and it's a reactant in the second one. So if you get rid of those and add them together, you get silver chloride plus 2 ammonias, making the complex ion AgNH32+ and chloride. And then K net for this one would be literally KSP times KF. When you add reactions together, you multiply the Ks. This comes out to be 2.9 times 10 to the minus 3. So even though it's still reactant favored, it's much less reactant favored than the KSP for silver chloride. So it's much more likely to get rid of the silver chloride by adding ammonia than if you don't add the ammonia. So this is kind of a positive use sometimes if you want to have cool glassware. And of course, that's what we try to do here at Mount Hood.
When solutions of silver nitrate and sodium chloride are mixed, insoluble silver chloride precipitates from solution. When we add ammonia to the mixture, however, the precipitate redissolves. When ammonia is added to a mixture of solid and aqueous silver chloride, the ammonia serves as a Lewis base. The complex ion formed consists of 2 ammonia molecules bound to each silver ion. Formation of the complex lowers the concentration of silver in solution, which changes the solubility equilibrium.
So it's not that the ammonia will get rid of all the silver chloride. Like you can see in the video in the bottom, there is still some solid AgCl left around, but it does a great job. All right, the ammonia again acts as a Lewis base. It attacks the silver of the silver chloride, the Lewis acid, and it's able to remove the silver as the complex ion from the silver chloride, which is really, really cool. So it will get rid of your pesky AgCl if it's coating your glassware. Kind of a cool thing. Ammonia can be all right. This is called coupled equilibria, by the way. The book uses this term, and it just means you're adding 2 reactions together. And almost always you're going to cancel one of the chemicals, like we canceled silver here. If you need to calculate the new equilibrium constant, you would multiply these Ks together to get the new value. Remember that if you flip a reaction around, you can go 1 over K to get the new value of that. Pretty chill. Here's another example of coupled equilibrium. We saw the formation of ZnNH342+ in the Le Chatelier's principal lab. So if you're curious about that, anyway, you can use the KSP for ZnOH2, zinc 2 hydroxide. It breaks down to zinc 2 plus and 2 hydroxide, the KSP 4 times 10 to the minus 17th. Well, if you do the same thing like we did in the last one, zinc and ammonia make this zinc NH342+ complex ion. There's the KF value for that one, 3.6 times 10 to the 8th. Now again, coupled equilibria just means you're combining 2 or more reactions to give some desired third reaction. We'll couple these 2 together. We'll be able to cancel the 2 zinc atoms, and you can see then that zinc hydroxide plus 4 ammonias makes the complex ion plus 2 hydroxides. K net, the K of this overall reaction, will be KSP times KF, 1.4 times 10 to the minus 8th. So again, still reactant favored, less than 1, but certainly not as reactant favored as the KSP value. So it makes it more soluble than it was before, which is kind of cool. This can be used to explain why hydroxides dissolve in acids. There's all kinds of kind of cool things you can do here with common ion effect. So anyway, common ion effect in some ways is just Le Chatelier's principle too. You can decide the best way that all this works out. But anyway, as long as you understand the idea of combining reactions to get some overall desired reaction, and you can multiply the Ks together to give the overall K, you are good to go. So that's the end of chapter 15. I appreciate you spending your time with me. There's the study guide and concept guide, which will go over more information. The equilibrium constants handout will list KF as well as KSP and the other Ks we've seen so far. There is a solubility guide handout, which will have more information on how to calculate things related to solubility as well. Thank you for spending your time with me. I do appreciate it, and I hope this has been useful and helpful to you. I hope you have a great day. Thanks for being here.